Let's take a massive leap right into 2 and 3 dimensions. Today, we're decoding the invisible mathematical rules that actually govern how objects move in our physical universe. Upgrading our perspective from those simple straight lines to see how the world really moves. Okay, here's our simulation initialization sequence for today. First up, navigating 3D space. Then, we boot up the kinematics engine. Third, we'll tackle the projectile paradox. And finally, we'll bend the rules with uniform circular motion. Let's get right into it. Section 1. Navigating 3D space. Building the digital grid. So the absolute core rule of multidimensional motion is separating your scalars from your vectors. Scalars? Well, those are your simple quantities, right? Temperature, mass, time. They just have a magnitude, a single value, and they don't point anywhere in space. But vectors possess both a magnitude, which is essentially their length, and a very specific direction. Things like displacement, velocity, and acceleration, those are all vectors. And this is where it gets incredibly useful, because it means we can take any complex three-dimensional diagonal movement and just break it down into simple, independent coordinates. So instead of dealing with some messy diagonal line, we split that vector into an x horizontal component, a y vertical component, and a z depth component. And here's the crazy part. The horizontal motion absolutely does not care what the vertical motion is doing. Mathematically speaking, they are totally independent. Section 2, the kinematics engine. Introducing time. All right, we start things off with a displacement vector. This simply tracks your overall change in position, and it completely ignores the actual path you took. So think about it. If you wander through a complicated maze for 3 hours, but you end up exactly 2 meters north of where you started, well, your displacement is literally just an arrow pointing 2 meters north. Oh, and importantly, this is always relative to your starting frame of reference. I mean, if someone was walking right alongside you the whole time, your motion relative to them would look completely different. So let's see how this all builds together. Tracking your position over a specific chunk of time, that gives us your velocity. Now, if we shrink that time interval down to a tiny instantaneous moment, boom, we get your exact instantaneous velocity. And if we shrink it again, tracking how that velocity changes over a tiny moment gives us your instantaneous acceleration. It's like zooming in closer and closer on the data. Now, here is a crucial point that trips a lot of people up. Acceleration isn't just about mashing the gas pedal. In physics, merely turning a corner alters your velocity vector, which means you are actively accelerating. Because velocity is a vector, literally any change to its magnitude, your speed, or its direction counts as acceleration. That's a huge perspective shift, and it's going to be absolutely critical when we look at circular motion in just a bit. Section 3, the projectile paradox, deconstructing the arc. When you capture a bouncing tennis ball with stroboscopic photography, you see this seemingly complex, continuous parabolic arc, right? It just looks like this single, beautifully complicated sweep of motion. But hold on, remember our rule about independent axes? Prepare to have your perspective shifted a bit here, because this complex motion is actually just an illusion. It's created by two completely independent one-dimensional motions happening at the exact same time. Horizontally, the ball is experiencing zero acceleration. The moment it leaves the racket, its horizontal velocity stays perfectly constant. But vertically it is in free fall, dealing with a constant downward acceleration from gravity. And we can actually prove this independence with a classic experiment. If you take a golf ball and drop it straight down, and you take another golf ball and shoot it perfectly horizontally from the exact same height, they will hit the floor at the exact same time. No way, right? But it's true. The forward momentum of the horizontally shot ball does absolutely nothing to delay its fall. The vertical motion simply doesn't care about the horizontal motion. So by breaking that initial launch into its x and y components, we're essentially hacking the physics of the real world. We get to solve complex projectile trajectories by treating them as two separate, highly predictable, one-dimensional equations. We just use the vertical axis to figure out exactly how long the object stays in the air, and we use the horizontal axis to figure out how far it travels. It's just a remarkably elegant solution to a multi-dimensional problem. Section 4. Uniform circular motion. Bending the rules. Okay, let's bend the rules a bit. Imagine sitting right in the center of the backseat of a car that's suddenly rounding a sharp curve. How is it that you can feel this intense force pushing you hard against the door, even if the speedometer needle hasn't moved a single inch? Well, your body is just trying to obey the laws of straight line motion, but the car is suddenly changing direction underneath you. Remember, because velocity is a vector that includes direction, constantly turning your vehicle means you are constantly accelerating radially inward, right toward the center of the circle. We call this centripetal acceleration, which literally translates to center seeking. Your velocity vector is pointing forward, sure, but your acceleration vector, that's a laser beam pointing straight into the middle of the turn. And the math behind this is surprisingly straightforward. Your center-seeking acceleration is directly tied to the square of your speed, divided by the tightness, or the radius, of your turn. Basically, the faster you go, or the tighter you take that corner, the more aggressively that acceleration has to pull you inward just to keep you on the circular track. So this completely demystifies why you feel compressed against a turning car door due to road friction, while astronauts experiencing the uniform circular motion of orbit feel totally weightless. It's all about what's providing that inward centripetal force. In the car, it's the friction of the tires on the road creating that center-seeking force. But in space, Earth's gravitational pull is what's constantly accelerating the space shuttle inward, curving its path perfectly to match the curvature of the planet below. As we power down today's explainer, I want to leave you with a final thought. If you really look around, the universe isn't just random, chaotic motion. It's this meticulously calculated grid of independent axes, relative reference frames, and perfectly predictable arcs. So the next time you throw a ball across the yard or take a sharp turn in your car, ask yourself, what invisible vectors are actively guiding your path?